I know. All right. That's enough about DC generators. So let's talk about alternators. DC alternators. What's the next picture? There we go. So unlike a generator, and by the way, you're going to have to take some notes because I don't have time to write a bunch of notes for you. So unlike a generator, an alternator has a stator, which is fixed, and a rotor, this spins. The stator, the part that stays in a generator, is called the what? In a generator? The field, okay, field poles, field windings, and the part that rotates is the armature. So in a generator, where is the electricity produced? In the stators or the rotor of the
Rotor.
In a generator, where is the electricity produced? The spinny part,
Turning part.
or the not turny part?
Turning part.
Break it down so you can understand me.
Turning.
Let's hear it. The armature. Okay. So now in a generator, it's backwards. Oh, sorry. Then an alternator. So an alternator, it's backwards. So the part that spins is the field. So in an alternator, the part that spins, the stator, the rotor, the part, oh, it's late. All right, the part that spins, the rotor, that spins, is the what?
Magnet. Electric field.
Better write it down.
Coil.
Write it down. There we go.
Magnetic
Okay.
field line.
So the part that spins, the field spins. The field spins. And in this case, the stator is where all of the electricity is produced. Well, that will provide some significant benefits. I think that's all the pictures I have. Yes, it is. All right, so we can go to here. So alternator. And then alternator. Alternator.
So is that motor still on the inside, right?
Yes.
And it's the rotor that spins, and
Yes.
but the electricity comes from the state.
From the stator. All right. I'm trying to go off my notes here really quick. So let's see. Alternators. One, they have a rotating field. And a stationary armature. Well, this does something really cool when you think about it. When you're talking about a generator, we have a commutator on the back of the armature, right? And what comes out of the commutator?
DC voltage.
How much?
As much as the voltage regulator allows.
All of the output of the generator comes through the commutator and out the brushes. So the brushes, so let's say I have a 40 amp generator. How many amps are flowing through the brushes? 40. So you have to have some pretty healthy brushes. Not only that, they're writing over commutator segments, which I showed you have what's in between each segment? The mica, which is called undercut. You undercut it about the same width as do depth, which is about 32nd or so. So you've got this mica, so you have all of these little grooves. So the brushes are writing over all these little grooves with massive amounts of amperage going through it. They do arc a little bit, so they're going to wear faster. Well, with an alternator, when you have a rotating field and a stationary armature, the brushes are going to slip rings instead. Let's see if I can have a good picture. I don't have a good internal picture. I was hoping I did, but I don't. So sorry about that. So in the back, we have some slip rings. And going back to like Monday, we talked about slip rings. And slip rings are just very smooth rings, like I showed you on the original armatures that we started looking at. We can go back up here and take a look at it. Let me see if I can find one. There we go, right down here. So we got these slip rings. Nope. We can look at this. And we had slip rings down here, right?
Yes.
Let me see, where else do I have some? What's that? Thought I had some good pictures.
No, it's commutator. Oh, here.
Ah, there we go. We got slip rings right there. So slip rings, they don't have any breaks in them. They're very smooth. And so the brush is just riding on a very smooth slip ring. So this looks very much like the slip ring setup in an alternator. There are two of them because what's going to happen is you've got, we can say a positive and a negative. And so the positive one is going to come in and go through the windings of the field and back out. And so all you need is little tiny brushes because the only thing that's flowing through those brushes in the slip ring on an alternator is what? The field current. Just a couple amps. So you have a 100 amp alternator. How much current is flowing through the brushes?
2 or 3.
Just a couple amps. So where then is all of the current that's being generated going out of? Out of the field, don't say field, you screw me up. Out of the armature, which is stationary. So if it's stationary, you can just wire it, right? You don't have to have any slip rings. You don't have to figure out how you're going to gate for something that's twists and something that's not twisting. So it's very simple. So you're just back to just some slip rings with just a couple of amps going through it. So, all right, have a rotating field and a stationary armature. Well, this eliminates the need, this eliminates the commutator. Eliminates the commutator. So commutators have poor brush connections, especially at high power settings. Eliminates commutator and instead uses slip rings and brushes on the field. The current through the slip rings, is only a few, it's going to depend on the field strength, only a few amps rather than the entire load, rather than the entire load or the entire output. So that means the brushes are going to last longer and there's no arcing. Well, no arcing and they'll last longer. How about that? So brushes last longer. Brushes last longer. So that's a big positive, right? That is one of the to me that is one of the primary advantages of an alternator. But then we can get just basically based on their construction, they're lighter weight. They work much better at idle, but they're not self-exciting. Oh, I know. Self-stimulating. Neither. They are neither. All right. So what else do we have here? Let me try to get all the main points. So main parts. Talked about them. What are my main parts? I need 3. So stator. Also called the what? Okay. And you know what the armature does. What else do we have? Also called the field. And we've got one other part in here that's kind of new. Rectifier or diode assembly. Well, the reason why we need a diode assembly is because within the alternator, just like the generator, we have multiple poles running around there. And we actually have multiple windings too within the alternator. As you'll find out, they can either be in a delta configuration or Y configuration, which I'm not going to get into right now. but that means that we have multiple windings, shall we say, that are producing multiple rectified DC. So it wants to make AC, but we have to rectify it. So if we only had one winding, we know it's going to look like that. But we have multiple windings, right? So multiple windings are going to, oops, that one kind of died off, bad diode. All right, so multiple windings in there will kind of even out, and we can pick off right about there, and it's going to give us kind of a little bit of a rippled DC, but it's like a spider. So, all right. And how did we achieve this in a generator? Through the commutator. So it was done, what I would say, mechanically,
Through the
right?
brushes.
But now we're going to use a diode assembly. I don't think I have a picture of a diode assembly, but maybe we can draw something here. So let's see. All right, so we got, over here I got the field. Over here I've got my, so field rotates. That is my rotor. Here's my armature with 3 windings on it. And I'll pick these windings off. And run them to a diode assembly. So, oh boy, I really asked for it now. All right, so diode assembly. So how many diodes do I need?
6.
Got 6 diodes. All right, so we'll connect my diodes. And let's see, we'll connect this one up over to this one. We'll connect this one to this one, and this one to that one. And then, let me think. Connect all these together. Right there, and these together. All right, and I think that would be plus, negative, that would be plus. All right, so getting rid of our commutator assembly, what we now have is this, this is rotating around, my field is rotating around this, creating exciting and creating current within the windings of the armature. And so if we follow this through, all right, so we pick up here, you can say this one's positive, and this one over here, we'll look at this one negative, oops, negative, negative. And so positives are going to come up here, and using, well, doesn't matter what we use. So positive's going this way, and is it going to go this way or that way? To my right or to the left? To the right. Remember, because diodes are sort of drawn with an arrow for conventional theory flow. So if this is positive, it's going to come out over here, go down to here. If this is the negative side, it's going to come up here, turn on the negative, go backwards and down here. So that's supposed to be negative. So when this winding right here is the one that's being excited, you can see how it rectified it out and put the positive over here and the negative over to here. And as it rotates around, it's going to, then this end is going to become the positive and this become the negative and so on around. And so there we go. So the diodes are going to do, well, I'm going to say 2 things. One, they're going to rectify it to a DC output, because what is being created in the windings? AC. So now it's going to be DC. All right, another great thing about diodes is if we look at the voltage regulator, because it still needs a voltage regulator, still have to regulate the field, nothing's going to change. The field, the stronger the field, the more the output, and if the output gets too much, especially the voltage gets too high, you got to decrease the field. Okay, so we saw that with we had a 3-unit, 3-part generator control unit, which consisted of a voltage regulator, current regulator, and a reverse current cutout. Well, this needs 2. It still needs to regulate the voltage output, and it still needs to regulate the current output. Now, in older ones, you can still find vibrating coil assemblies. But in newer ones, it's just a solid state little chip. Basically, it handles all of that. But interesting enough, no reverse current cutout is needed. Why?
Diode.
Diodes. So current tries to roll backwards, just hits a diode, it's done. It's got six big diodes in there for winding like that. So the diodes rectify and act as a reverse current cutout. So yeah,
Why do you have 6? Does it have to be 6 for all alternators?
you can have more, but as long as I have 3 windings, so I need 6. You need 1 for each winding, and they're all wound this way, pretty much. Yeah, and all the ones I've ever seen are just 6 diode. So you need 6. Write that down. You need 6. All right, you need 6 diodes. I'll write it down. Then you need 6 diodes. That wasn't drawn by accident that way. Diodes rectify the output, and eliminate diodes. Eliminate the need for a reverse cutout relay. Reverse current cutout relay would be the more appropriate term. Wow, did I really just go through the whole thing? All right. There's not a whole lot more to say about it. That's the wonderful thing about once you understand a generator and a voltage regulator, you just simply apply it very quickly to what comes down the line. That's why I spent 2 days on generators and the voltage regulator, and now I can just say, well, there's an alternator. It pretty much works the same way, except you reverse what spins and what stays, and you don't need reverse current cutout because you have diodes, and there's not much more to it. I had some interesting stuff. How is this driven? Belt or gear chain? Get out of here.
What's the purpose of condenser? Which in our alternator?
Okay, so obviously I made it very simple. You can also add a condenser.
Yeah.
So what do you think a condenser is going to do? Let me see if you can figure it out.
Became,
You asked me and you're new?
I'm, you know.
Okay, so
Don't play dumb now.
yeah.
So, yeah.
See this guy right here?
Yeah.
It's to help him out especially. So when you use a capacitor in DC, what did I say that helped? Smooth stuff out. So on the peaks, it's going to absorb the peak, and on the valleys, it's going to give back out. So where it looks choppy like this, well, when I got all done, boy, it looked pretty much like that. So it looked pretty good. So yeah, I just needed to add a capacitor, and then it's going to be all better. There you go. So
That didn't help your drawing, Kevin.
my drawing's beautiful. So, you have no excuses. So if I draw it, I know you can draw it.
So I look back at my notes and I go, what the hell is that?
I know, but it looks just like mine. Okay. One of the things you might be expected to do is, on your oral practical, inspect a generator alternator. They always lump together. Inspect a generator alternator installation. Very common project. What are you going to do?
Make sure it holds it on and the belt's not broken.
I like that. I like that. Again,
Wiggle
remember,
some stuff.
this is not the way to do it.
Use your hand.
I'm done. Because I got that all the time as a mechanic examiner. You're done. Well, did you look for anything? Yeah, I'm done. Verbalize. And just verbalize that stuff. I'm looking at the mounting.
Mounting.
Now,
Belt tension.
I never asked, what do you mean mounting? What do you, if somebody said that, I'm like, okay, they said the words. We're good. We're good. I don't ask what specifically. That's the nice thing about testing here versus when you get the mechanic examiner. It relaxes a little bit. I want you to be well prepared. So, all right, checking the mounting. Checking the, what was the other thing?
The drive belt.
Drive belt. What are you looking for in the drive belt?
Racks.
Beautiful.
Tension.
Just throw tension. What should the tension be?
Depends on the
Whatever the
manufacturer.
manual.
Whatever the manual says. That's exactly it. So So if the examiner said something like that, well, what should it be? Whatever the manual says. Well, maybe you should, the best way to say be, and I want to check belt tension. Do you want me to look this up in the book and check the tension? I'd be happy to do it. And as a mechanic examiner, you know what I'd say every time?
No.
No, you're good. Unless the project specifically said, check belt tension of an alternator. Then I'd say, yes, please do it. But otherwise, it didn't. The ones, I did it, check an alternator, generator, installation. So there you go. So it's assuming it's belt driven, like this picture had it. But what if it's not belt driven? What if it's gear driven?
Or change it.
So by the way, belt tension is usually about a 1/2 inch deflection.
A half inch.
Yeah.
When you
How much
mean
weight?
deflection.
Don't, I know, it's with a certain amount of, so when you put a certain pressure on it right in the middle, it should deflect about a 1/2 inch.
Okay.
But you got to know what that certain poundage is. I don't know
Does
offhand.
the twist test not apply on airplanes?
I'm not familiar with the twist test. I've
Okay.
always the deflection
That
test.
answers the question.
So, okay. But, this one's down here like that. So do I have to worry about oil leaks?
Yes.
No.
Where you got oil from?
Yeah.
Well, okay. Do I have to worry about oil leaking through the generator from a bad seal?
No.
No, unless you want to talk about one of the seals around the engine leaking
yeah.
into the oil. Yeah, and that's a whole nother problem. But if it's gear driven, like a lot of Continentals, they're gear driven, on the other side, but they're gear driven right where the cylinder is. It looks like it's like 6 cylinders and a 7th. What that's for. It's for the alternator drive. And so they're driven inside. So yeah, then you have to worry about the seals and make sure that's not leaking. So no oil leaks. Don't forget to take off the band, the inspection band in the back, and take a look at anything. Also, and I don't have this written down, this is something that really gets overlooked a lot, and you should remember to do this. On most airplanes that have an engine-driven, well, they're all engine-driven, alternator that is gear-driven, you're not going to see this part right up here. I hope you can see what I'm looking at, because it's going, yeah, you're not going to see a pulley because it's going inside the engine. But what you are going to still have is you're still going to have this fan assembly. It's going to look a little different, but you still have a fan assembly. And one of the tests that I do always, all the time, every annual, is put your fingers in there and see how far that fan assembly moves without moving the propeller. Now, you're not going to move the prop with your finger touching the fan assembly because it's small and plastic and gear driven, but it shouldn't move a whole lot. There's going to be some movement, but especially on the smaller Continentals, like on the 150s, they can get to moving a lot. And when they move a lot, it means that the drive bushings inside the engine, which are made of rubber, are going. And so you want to make sure that you take that out and change these rubber bushings, which cost probably the cheapest thing on an aircraft, about $5 each. And they last about like a $5 part. And so you have to change out those little bushings. So you want to make sure that there's not a whole bunch of slop built up in the drive coupling. Drive coupling slop. Just a little bit. Just a little bit.
This is a twist back and forth, or is this like an up and down play?
No, because the alternator is bolted to the engine. So the alternator should not be moving up and down. It's locked to the engine, right?
I just replaced an alternator.
I'm talking over here. So, so it's locked to the engine, but it's driven inside, internally, right? And so you want to see how far the alternator will turn. The armature, not the armature, the rotor will turn without the engine turning.
So if the engine turns, then you have a big.
It would be like seeing how far this thing right here would rotate, but the belt's stuck on there. So now it's Steve's turn.
Oh, I just replaced an alternator. I paid $1,200. They could have been a $5 part, and they just like paid $1,200 and we bought me a new one.
No, what was wrong with the alternator?
They said the bushings were bad.
Yep. Now, in all fairness, it was a 150, right?
Yeah.
It's not easy to get that alternator out. It's almost because it shares the same gasket with the. Now we're getting off subject. Sorry. Shares the same gasket with the tack drive, so you have to cut that, split it, put that in, and usually you have to take the magnetos out to get to all the hardware because it's buried. So you have to pull both mags, and then the generator,
So then they
then
gotta
fix
retime
it, put it back in, then retime it, put it together. So it's labor. You're paying a lot in labor.
Okay, because they gave me a whole new one, and I was like,
Wait, do you have
said
Thursday?
that, and they told me clearly, like, Thursday, the bushings are bad, there's play. And I was all like, whoa.
There are two different couplers, but one of them's cheap, one of them's very expensive.
Okay, 'cause they ended up just buying a whole new one. So we asked if we could overhaul it, and they're like, no, it's worth just getting a new one. We did. So
I replaced the bushings in mine. It cost me all of about $20 in bushings.
Well, what would have been labor without you doing it?
It took me about an hour or so to do it.
So really, I should have only been charged like $300.
I don't know about that. Anyway. Steve's mad now.
There's a reason we're still in business.
Okay. Hector probably has a legitimate question.
When you put them in, is it hard to like line it up or should we just...
It's an aircraft. Nothing's easy. And then you drop one of the bushings out, and it falls down into the engine, and then you're going to hate your life. So, by the way, big bore Continental engines, they have the same style of bushings to drive magnetos, and they're up top, and they do tend to fall. So if you're not really careful.
So like I know on aircraft, at least on this picture, there's one belt driving the alternator.
Yeah.
Compared to like automotive,
Yeah.
like one belt can drive like 6 different employees. Is that like in the case
That's
like
a
here?
17 belt.
Yeah, I was gonna say I'm not familiar with any aircraft that uses a serpentine belt, unless it's like some of the light sports and stuff. They'll get into it. Well, I guess our 172 out there, it's got a serpentine, but it's also got a Mercedes-based diesel engine conversion. So your Lycomings and Continentals do not. Let's just put it that way. But you know what people love to do, since we're on this picture? So in order to change this belt, see that belt's about, would you say about like that? And I'd say the propeller's about like that. So how do you suppose they get that belt over and around the propeller?
Cut it.
Use
One at a time.
One at a time?
Apart, you melt
One
it
at a
back
time.
together.
Stretch it.
Take the prop
The
off.
blades are this long.
You cut it.
You
Oh
cut the
my
belt,
God.
Cut the belt.
you put it around it, and you melt it back together.
There you go. So you got to take the prop off to change that belt. And let me tell you something. That prop is not fun to change, because what you can't tell is those bolts right there are really hard to get to torque. You need an adapter. You got to fight it. And the safety wire, this hasn't been safety. There's no safety wire there. The safety wire to do that will take you some time. It is one of the worst safety wire jobs in general aviation right there. So what people will sometimes do is they'll put 2 belts on. So one belt goes here while it's running, and the other one, they just kind of wrap back in here and tie it up and safety wire it to this little lifting eye right there. So here, this belt is running and operating, but this one just gets to sit here on top of an engine with cylinders radiating 400-degree heat on it,
Oh my God.
and bakes and bakes. So when this one breaks, you can just simply put this one on until it breaks in the next 10 minutes too. So then you buy 2
You
and put
don't
them
think
on.
they really think about that by the time they take that off of like, ooh, this is hot.
I see it all. I've never done it. I see it all the time. I've never talked to anybody. So, hey, if you're on YouTube, you can leave a comment below how well it worked for you and how much longer the second belt lasted.
Kevin,
So,
you gotta get viewers before that happens.
I'm always hopeful. All right.
It's in a lot of work for that.
Yeah, so I don't know. But then again, I was in the business of, changing this stuff, so I wasn't going to make it easy. Well, I wasn't going to sell somebody 2 belts, one to bake and one to use. Just couldn't do it. All right. I can always tell when you guys get excited about the topic there. Okay, so what else we got? I've got a bunch of ways to test it. We just don't have time to kind of get into control.
Wire delta.
Yeah, wire delta windings, but that's not what it's going to.
How we can recognize the
Okay, so there's 2 different windings, a Y or a delta. You know what? I don't care. As a mechanic working out in the field, doesn't matter. Be a Y or a delta or an alpha or a beta. It just I don't know. Are all of the Greek alphabet, and it doesn't matter. They all work the same, and you treat them the same, and you test them the same, and you operate them the same. So let's see. Oh yeah, we don't have time to get it. Test for rotors for open. You might want to see me about some of my notes because you have an alternator that doesn't work out there. Testing rotors for opens and grounds. Testing the stator. Why is that funny? Picked one out of the shelf that didn't have a tag on it. It didn't. Oh, it did have a tag, but we opened it up. It was clearly not working. So he fixed it, but we still have some other things.
You got another 2 days.
Yeah.
Which way does the alternator spin?
Both ways.
That's true. Yeah, Saturday. Saturday the one.
It'll work either which way, or it won't work at all, right?
So K-Dog, I got a question.
Waiting all day to say that.
What happens if you fail the test on Friday? Because you're gonna be gone.
We're taking it tomorrow.
It was all for no bill.
It sounds like it's not my problem.
That's true, but I'm just saying what happens.
And do we fail the class?
No, I'll be around. I'm always around. By the way, since you call me K-Dog, you know what they used to call Katie?
K-Dog?
Huh?
K-pop?
Who's K-Pop?
There you go. Matt.
Hey, what?
All right, one of the questions I ask people when we're over at the alternator stand or the generator stand is you hook up your alternator generator and I turn it on. When I turn it on, there's a voltmeter. And when I turn it on, I turn on the machine. Now, you also work with me on this. Some people fail to recognize this. The machine is simulating the engine, okay? So, I know, it's crazy. So I turn on the machine,
So it's a belt breaker?
and I have a voltage. What does the voltage read when I just click on the master? And the generator's not running, the alternator's not running.
Battery power.
Okay, I'm reading battery voltage, which should be about,
A little over 12.
okay, a little over 12 is fine by me. So a little over 12. Exactly. 12.6. All right. So how do I know when I turn on the motor that drives the generator or the alternator that the generator alternator is working? Voltage should go up above battery voltage. Same thing in an aircraft. If the voltage remains about 12, 12.6, and you're like, God, I don't know if the generator alternator is working. Guess what? It's not. All right? So it's got to go above the battery voltage. So that's why I ask you, hey, how do I know if this is going to work? Simple. The voltage meter is going to go above the battery voltage, and then it's going to work. All right. Calm down. I still have 4 minutes.
So 4 minutes to 3 minutes.
So I'm just going to stand here quietly while you sit there.
Quiet time.
Yeah, it's my quiet time. All right.